Okay, everybody, welcome back. Before I begin, any questions? Um, as I mentioned last time, we are really have just two chapters left. The next chapter probably take two, at the most, maybe three sessions. And then the 15th chapter 15, that's probably one session itself. So we're probably looking at the next four sessions that we will have a Zoom lecture, but we have a lot more days left. So roughly maybe about one, maybe two sessions toward the end that we're going to set up for study sessions. So I will be here. I'll repeat that. I will be here for the time that I'm allocated, and then you can come in for, treat it as an office visit and ask any questions. We can go over any of the problems, so forth. Okay, so keep that in mind. If you have any questions, start making a list, and we can bring them to those study sessions and go over them. All right. Any questions? All right. So, well, let's start off with this particular chapter. Now, what this chapter entails is called intermolecular forces. Now, when we mean by intermolecular forces, we are talking about, look at the prefix, INTER, okay? The prefixes here are inter, and then forces, interactions that are occurring, and then of course we're looking at molecular forces. So what this means is the forces involved with the molecules with other molecules, intermolecular forces, as compared to intra, okay? Intra, meaning those intramolecular forces, those are forces within the molecule in itself, okay? And the intermolecular forces, those are forces with other molecules. How they interact is a function of the polarity of that molecule. So here we go. Remember, we were talking, we did a lot of work on determining we talked about polar bonds, and then we looked at the geometry of these molecules. We used the general formula ABE to determine the geometry. Based on the polar bonds, we talked about how molecules with all nonpolar bonds ends up with a nonpolar molecule. And then we talked about those compounds that had polar bonds that did not cancel out. Polar bonds that did not cancel each other out, resulting in an overall polar molecule. And those molecules that had polar bonds that did cancel out each other, resulting in a compound that was a nonpolar. Okay. We need to go back and refresh your memory on that, because once we define the molecule, determine what type of polarity that molecule has, then we can talk about assign to them what type of intermolecular forces these molecules have. Okay. Now, with respect to intramolecular forces, we're just basically talking about what type of bond they have. Is it a covalent bond? And if it was covalent, is it a polar covalent bond or a non-polar covalent bond? And then the other one was the ionic. Okay, so intramolecular forces, straightforward, what type of bond? Okay. With the inter, when you have to determine what the whole molecule is doing, and assign it is either as a polar or non-polar, and then from that information, we then further assign the type of force that they have. Once we do that, once we have assigned a force to an individual compound and what it has, we then can do a compare and contrast with other molecules. So we can look at other physical properties uh, and compare them with, say, two different compounds. Now, we can't give absolute numbers like things like boiling point, okay? We can't say, well, this compound's gonna have this absolute boiling point. However, what we can say is when we compare compound A and B, and depending on the polarity of the molecule, we can determine which molecule A or B will have a higher boiling point based on the intermolecular force that we assign to it. Okay. All right. So inter versus intramolecular forces. So a little more information about the interforces. So if we look at, let's say, these a molecule here, this diatomic molecule, okay, has two atoms. It's a compound, right? So within the molecule are these intra forces. That's what type of bond it has. Okay, so it's one's there, one's here. The type of bond. Oh, went too far with that eraser. Let me erase that. Okay. Now, the interactions with other molecules, and denoted here by the dotted line, represents what the intermolecular forces are, forces between molecules. Now, as a general guideline, as a general rule, if that force, okay, it's not a bond, keep this in mind, it's not a bond, it's denoted by a dotted line. It's not a bond, though we have one force that we give it the name bond. You may hear as a bond, it's not a bond, it's an interaction. If that interaction is strong, okay, and it's related to, all this is related to energy too. If that intermolecular force is strong, and if we put energy into the system, like heat, okay, and if that intermolecular force is strong, then it's going to take a lot of energy to break up that interaction, resulting in a higher boiling point. And that's what we're doing is when we heat something. Take example, water. You know, we have water in the three stages, in the three physical states. We have solid water, ice, okay, where molecules are all rigid. And then we have it liquid state, where the molecules relative to each other are somewhat not as ordered as a solid state, but are flowing relative to each other. And they're still close together, okay? And then you have water in the vapor phase, where the molecules are totally separated from each other, not close interaction. And you know that if we take ice and we put energy into a cube of ice, we heat it up, what does it do? It melts, right? And if we continue to heat that ice, what does it do? It evaporates. And so that's the energy when we heat something, is if that interface, that interaction is strong, very strong, it's going to take a lot of energy to break up that interaction. And water does take a lot of energy, and because water takes, you know, to melt it, it's at 0 degrees to go from solid to liquid. You got your that happens at 0 degrees. Now to get it to boil, we have to bring it up all the way up to 100 degrees Celsius. That's a lot of energy. So that takes a lot of energy to get it to boil. But if you look at, let's say, you may be familiar with this, rubbing alcohol, okay? Rubbing alcohol, which has a lot of similar properties with water as far as polarity, it evaporates fairly easily. You put some on your hand, you can feel it evaporate because those interactions with the molecules with each other, the intermolecular forces of the alcohol compared to the water are much less. So the alcohol evaporates much more easier and quickly at a lower temperature than water does. Water requires 100 degrees temperature. Ethanol, drinking alcohol, that requires about 78 degrees in temperature for it to boil off, okay? Much lower than 100 degrees because, again, though the properties are similar with respect to polarity, they're slightly different, so it does require less energy for the alcohol examples I used than compared to water. And all we're doing is breaking up those intermolecular forces. We are not breaking up the intra. The intra means that we are breaking the bond, okay, which would take a lot more energy to do than just the intermolecular forces. Okay, that's the big difference. Okay, intra, a whole bunch of energy to break up that bond. Inter, not so much. Okay. All right, so we got to review the polarity of the molecule and talk and review about polar bonds and nonpolar bonds. Okay, because it's very, very crucial with respect to this particular chapter. All right, so bonds versus intermolecular forces. Now let's take the example of HCl molecule. Now, the hydrogen chloride bond is a polar covalent bond. That is the intramolecular force of the molecule of hydrochloric acid, HCl. Okay, a polar covalent bond. Now, with respect to interactions with other molecules of HCl, we have the intermolecular force, and it has a specific name. In fact, there's only 4 types of forces that we're going to work with, that we're going to utilize to describe the type of force that's involved. Okay, there's only 4. So here's 2 types of forces. Now, what's happening here is the fact that all molecules either have a permanent dipole or a temporary dipole. Recall when we talked about dipole, 2 poles. Remember the dipole arrow that we had, okay? Where we had a partial negative and a partial positive side. Okay, some molecules, depending on the compound, had a permanent dipole. So it had permanently had a partial positive side and a partial negative side. Now, because of that, the nature of the beast is that with another molecule, it is the partial negative side will interact with the partial positive side of another molecule. Okay, so here's the intermolecular force occurring, the INTER, the intermolecular force interactions occurring between molecules, and that is because of the dipole that it has. Okay, now the other aspect is, so that means that, all polar compounds that have a dipole are going to have a certain type of intermolecular force. So what does that mean for nonpolar species? Well, they too have a particular type of force, but it occurs because what they have is a temporary force. Okay, it's a temporary temp dipole, okay, versus a permanent dipole for polar molecules. Okay, so what do I mean by a temp dipole? Well, let me tell you. The best analogy I can think, example I can show you with respect to nonpolar molecules and how they get a temporary dipole is, I'm sure someplace, sometime, you have taken a balloon and you probably rubbed it on your head and then put it on your chest and it stuck, right? Or have somebody do that. Or if you haven't seen it, try it. Get a balloon, blow it up, rub it on your head, and then put it on your chest, and it will stick. Now, it's not going to stick there all day. Eventually, it's going to fall off. Second of all, it's not like magnets where the attraction is pretty strong. It's an attraction, but it's fairly weak attraction. Okay, but it's also temporary. And what's happening is this: as you take that balloon and you rub it on your head, your body, your hair, are loaded with, guess what? Electrons. There's electrons all around us on the surface. Okay. I'm sure you woke up someday and your hair is like poof, especially on like in a winter day where kind of the atmosphere changes a little bit. There's a little spark going on in the air, right? Or you're dragging your feet on the carpet and you touch something and you get zapped. Okay, that's because as you drag your feet on the carpet, you start to build up electrons. You transfer electrons from the carpet onto you, and you build up a charge. That's what happens to the balloon. There's tons of electrons on your head. As you rub it, you're transferring electrons from the surface of your head to the balloon. Now what's happened on the surface of the balloon, there's a lot of electrons, which have, remember, a negative charge, right? And also remember, negatives do not attract to other negatives. Negatives repel. On the surface on your chest, and like I stated, all around you, you have electrons. So what you do is you bring that balloon onto your chest. The electrons that are on your chest get repelled by the electrons in the balloon, and in essence, spread and move away from the surface, resulting in a positive property on the surface of your shirt. Becomes more positive, like a partial positive of the dipole. We got the negative of the balloon. What's going to happen? It's going to attract, and your balloon is attracted to your shirt, and it stays there. No different than, if you're wearing, for you ladies out there wearing your dress, you got static cling, or even for guys with pants and they kind of loose fitting pants and they kind of cling to your pant leg. Your leg is because of the electrostatic charge. Okay, and what you have done is, in essence, created a temporary dipole, and that's what is happening with nonpolar molecules. Okay, they get a dipole, a partial positive and a partial negative, but it's temporary. It is induced. Okay, it is induced. All right, so the first type of force that we deal with are called London dispersion forces. Okay, London dispersion forces. The second type are the dipole forces, or DDF. Okay? And then there's a third type, which is basically a dipole force, like number 2, but with an additional aspect to it. It is called hydrogen bridging force. Okay, you may have also read someplace where they call this hydrogen bonding. As I stated before, these forces are attractions and they're not really true bonds. So they're trying to get away from hydrogen bonding naming and give it the name of hydrogen bridging force. It's a special type of dipole force as listed in number 2. It only occurs when you are dealing with hydrogen, okay, with hydrogen, and only 3 specific, when hydrogen is bonded to 3 specific atoms. But more on that here in a bit. And I'll explain a little bit more in a second. And then the fourth one is called the ion dipole force. Well, normally what happens with number 4 is we're looking at ionic compounds, hence the term ion. And then the dipole comes from, most of the time, the majority of the time, we're dealing with water, okay? Because water has a dipole force. There's a dipole in here. And then we'll also have that extra special force that we'll talk about here in a second. So this is the interaction of ions that have been that are what we call solvated with water molecules, okay? And so number 4 only pertains to cases where you have an ionic compound and water, which means that you're dealing with aqueous systems, okay? Aqueous systems. All right, now for London dispersion forces, any compound that has been designated as a nonpolar compound, okay, the only force they have are London dispersion forces. Okay? And so here we go. We got to learn, refresh our memory. How do we define polarity of the molecule? Okay, well, we look at the bonds. And so if any molecule has nonpolar bonds, like the carbon-hydrogen bond, remember the carbon-hydrogen bond? That is a nonpolar bond, okay? So all hydrocarbons are nonpolar, okay? All the diatomics are nonpolar. All the diatomics have no fear of ice cold beverage, okay? They are nonpolar. Therefore, those compounds, the only intermolecular force that they have are the London dispersion forces. So all the other number 2, 3, and 4 have nothing to do with nonpolar molecules. Okay. Dipole forces. Well, first of all, it has to be a polar molecule. Okay. And so having a polar molecule, remember that was the example where I used the example of an AB bond. Okay, meaning there's 2 different atoms that are bonded together. Automatically, you have a polar bond unless it is a carbon-hydrogen bond, which is automatically a nonpolar bond. Okay, now just remember the AB. I can't overemphasize that because sometimes students forget. Well, how do I know it's polar? Well, just look at it. If I have 2 different atoms bonded to each other, automatically I have a polar bond. That's it. I don't know what other way to tell you, unless it's carbon-hydrogen, okay? And the reason carbon-hydrogen, to refresh your memory, why it's not a polar bond, is simply because the electronegativity of carbon and hydrogen are essentially the same. So they act like the diatomic molecules. The diatomic molecules, the electronegativity are both the same, through the same atoms. So there's no unequal pool of those electrons, and therefore it's no dipole. Okay, so that means that any other example, AB, and I use in generic terms, AB bond, I got a polar bond automatically. Now, refresh your memory about electronegativity. Remember, electronegativity was the affinity of a bonded element or a bonded atom, that would the affinity for the electron. So if it had a strong, higher electronegativity compared to whatever is bonded to, it's going to pull those electrons onto itself much more so than the other element that's bonded to. And it's based on the electronegativity. And remember, fluorine is the most electronegative element. And so we use fluorine as our benchmark. And so to compare 2 different atoms that are not fluorine, carbon and nitrogen, we just look and see, well, who's closer to fluorine? And whoever's closer to fluorine has a higher electronegativity, and therefore it would pull the electrons onto themselves and therefore create a dipole, a permanent dipole, and therefore has the forces of the dipole force for them, okay? All right. Now, number 3 is called hydrogen bridging force, which is a dipole force. However, it's a little bit stronger and it needs to be in its own little category. But those are only for examples of hydrogen bonded to nitrogen or oxygen or fluorine or fluoride, okay? I call it H, not NOF, not on file, to help you out. HNOF, okay? That is, there's a dipole there, okay? Between the nitrogen and the hydrogen and the oxygen and the fluoride, there is a dipole, but because it is specifically hydrogen, it's an additional stronger force, okay? And we call that hydrogen bridging force. And the example for we did dipole would be like hydrogen chloride, what we were talking about earlier in the previous slide. HCl does not have hydrogen bridging forces. It only has dipole. It doesn't have hydrogen bridging force because it's only when hydrogen is bonded to either nitrogen, oxygen, or fluoride. Okay? All right. Now, with respect to strength, hydrogen bridging is the strongest of the three. London dispersion forces is the weakest. I call that number 3, Roman number 3. And number 2 is somewhere in the middle as far as strength. Dipole is somewhere in the middle with respect to London dispersion forces and hydrogen bridging. Okay, so hopefully you can start seeing where I'm getting to. Earlier I said the boiling point was an example where we were putting energy into the system. And if the intramolecular forces are strong, then it's going to take a lot more energy to break up that intramolecular forces to get something to go from either solid to liquid to gas. And so when I'm comparing two different molecules, if one of them has been assigned London dispersion forces and the other one has been assigned hydrogen bridging force, well, now I can do a relative comparison between in some of the physical properties like boiling point. Any London dispersion forces, because that force is weak, will have a much lower boiling point than, say, another molecule that has hydrogen bridging forces, because that force is stronger. Okay? All right. Oh, excuse me. So basically, we think about it 1, 2, and 3. We're dealing with covalent compounds. Okay? That's it, covalent compounds. Whereas number 4, we are dealing with two separate systems. One, an anionic compound, okay, and a solvent, which most of the time is water. So aqueous systems. All right. So as I stated before, London dispersion forces are temporary, okay? And this is the attraction between nonpolar molecules. And so what's happening, like the example of the balloon and the electrons, is that as the molecules come together, the electrons of one molecule are pushing the electrons of another molecule away, creating a partial positive area, and therefore resulting in an attraction. Okay, weak attraction, but nevertheless an attraction. Okay. Now, with respect to London forces, so you might be looking at, let's say, two different hydrocarbons. Okay. Well, the fact that they're hydrocarbons means that the London forces for both of them have London dispersion forces. But if we need to compare within the same molecule, within the same hydrocarbon, the molecules that are bigger, the nonpolar molecules that are bigger, would have more London dispersion forces. Okay, think about it this way. For example, we have methane, which is the smallest hydrocarbon that there is. We know that methane is a gas. Now, hexane, which is a a H 14, I believe. Yeah, 14 is both of them are hydrocarbons. Both of them have London dispersion forces, but hexane is bigger. Okay. And hexane, whereas methane is a gas, hexane's a liquid. Okay. And we think about it for a second. Because methane, when we compare methane and hexane, methane's small compared to hexane. Methane has one carbon, hexane has 6 carbons and more hydrogens. So there are more interactions occurring for hexane, resulting in hexane, those forces which are dipole-dipole, there's more dipole forces resulting in that hexane becomes a liquid. Okay. Whereas methane is a gas. And, that's true for these forces that occur between hydrocarbons. And that's why some, like a lot of fatty acids, on one end of the fatty acids, they're very long carbon hydrogen chains. And depending on how their interactions, a lot of them are the bigger they are, the more solid they have. So you have like vegetable oil, okay? But you also have liquid vegetable oil, and you have solid vegetable shortening. Okay, they're all hydrocarbons. Okay, but the vegetable ones are bigger, resulting in more London dispersion forces, resulting in a solid material compared to the liquid, less forces of the liquid itself. Okay. And all of it is all related to, guess what? Electrons. Okay. These crazy electrons again, all right? These are interactions with electrons that are changing the properties or determine the properties of the molecules. All right, so this diagram here kind of shows you what's going on, sort of like the balloon example, where you have two nonpolar molecules coming together. The electrons from one result in pushing the electrons away from another, resulting in a partial temporary positive side and a partial negative side. So you can see how these molecules line up with other molecules because you're creating partial positive, partial negative groups, and you can see how they all line up. Much like magnets, if you line them all up, they're going to be attracted to the south and so forth. Okay, but the intramolecular force, the LDS, London dispersion force here, compared to the other two, is weak. Okay, and it doesn't take much energy to break that up. Okay, not much energy to break that up. Now, with respect to dipole-dipole, let me back up for a second. When it comes to nonpolar molecules, that dipole is temporary. That's the important thing to remember. This is a temporary situation, okay? Simply because the movement of electrons within the molecule. As compared to the next example, where we actually have a polar bond. And we have a permanent situation where we have permanently on one end is a partial positive side and a partial negative side. And that's the nature of the beast of the bond itself. Okay. And so we use the example here of hydrochloric acid, or HCl, where the chloride is a lot more electronegative. This is a polar covalent bond. Okay, so there's bond sharing going on here between the chloride and the hydrogen in that bond, but the chloride has a lot more electronegative than the hydrogen, and so we end up with the electron density being pulled toward the chloride, okay, and resulting in a partial positive on the hydrogen side and a partial negative on the chloride side, okay? because the differences of electronegativity, the delta electronegativity between the two elements, the change being that there's the difference, I should say, not the delta, but the difference. All right, that results in this interaction here, denoted by this dotted line, okay? Because the partial negative will be attracted to the partial positive side of another molecule. Now here we're showing you the picture two-dimensionally, but remember, we live in a three-dimensional world. And so, this is going on, above and below and behind and up front, in all three directions. And so there's a lot of interaction going on. And it kind of actually puts a little bit of order into the molecule itself. Yes, there's flowing back and forth, but because of the interaction, there's a little bit of order involved in the way things are lined up. But, think of it, like I said, three-dimensional. It's not just linear here. We live in a three-dimensional world. So, point number one is what for dipole forces, they're stronger than London forces. And second, point number two, in order to have dipole forces, it must be a polar molecule. Okay? And keep in mind that you can have polar bonds, but you end up with a nonpolar molecule. Okay? And that's because the polar bonds cancel out. So carbon dioxide, recall that example there with carbon dioxide where we ended up with the Lewis dot structure that looks like so. And we end up with a dipole going from the carbon to the oxygen. So we have a partial negative on the oxygen and two partial positives on the carbons. Okay. The result being that this molecule, carbon dioxide, becomes nonpolar. Since it's nonpolar, the only force they have to deal with are the London dispersion forces, even though they have polar bonds. Okay, now hydrogen bridging forces. Very similar to the dipole forces, but the exception is this is with hydrogen bonded to nitrogen, oxygen, or fluoride. And that results in a much stronger interaction compared to simply a dipole interaction. So water is a very polar species, H2O. And second of all, it's hydrogen bonded to oxygen. And so this interaction occurring here, this intermolecular force occurring there, is much, much stronger compared to the intermolecular force of HCl, the example we just did earlier. Okay? Very much stronger because, and if this could have been also nitrogen or fluoride. So there's only three types of compounds, well, three types of bonds that deal with the hydrogen bridging force. And again, very strong interaction because it's occurring, again, three-dimensional. So these forces get pretty strong. And so when you're heating this, when you're heating water, it requires for you to get up to 100 degrees Celsius to get that water to boil. It's because what you're doing is you put energy into the system, you're trying to break that up. You're trying to break up the interaction. Right? And that's why the interaction being so strong, that's why it takes a higher temperature. But again, we are not talking about bonds. These are forces. And so, yes, the hydrogen bridging force is much stronger than the London and dipole-dipole interactions, but they're nowhere near the strength of an actual covalent bond, or for that matter, an actual ionic bond, okay? And also keep in mind that even though we talk about ionic bonds, they're not a true bond. So just to refresh your memory, remember when we have, let's say, sodium chloride is an ionic bond, but the difference is here we have a full charge on the positive on the sodium and a full negative on the chloride. And it's basically like two strong magnets coming together and attracting to each other. We call that, remember, electrostatic attraction. Very strong electrostatic attraction. And so the strength of it is such that it is considered a bond, so hence ionic bond. Though there are no sharing of electrons like there is with covalent bonds. Okay, a lot of this I'm rehashing to you because we try to bring I'm trying to bring what we've been talking about in the previous chapters and kind of put it all together here. All right, then finally, the last type of interaction of force is the ion dipole force. And so here we're talking about it's an interaction between a polar molecule, which at 99.99 times it is simply an aqueous system. Okay. And then we have the interaction between a polar molecule, which is water, it's a very polar molecule, and a fully charged ion. And so you can see here the diagram that shows the full charge of the positive sodium ion, and then around it is surrounded by the partial negative charge of the oxygen in water. And then on the other side, if this was, for example, sodium chloride, table salt, on the other side, we will have the chloride ion that is interacting with the partial positive side of the water molecule, the hydrogen side, okay? And so all this, again, occurring all around three-dimensionally. It's a very strong force. All right. Okay. Any questions at this point? All right, so let's summarize the differences between the bonds and the forces, okay? Kind of put it all together for you. So when we talk about the bonds, remember that we are talking about the intramolecular interactions, forces, okay? When we're talking about the forces here, we are talking about intermolecular forces. So intra meaning within, intra meaning not within, outside, externally with others. And so when we talk about the bonds, recall that we have three types of bonds. We have ionic bonds, which is a combination of a metal and non-metal. Okay. That question was asked in some of the assignments we had, and the question was to distinguish between an ionic bond and a covalent bond. And basically what we're looking for is that simple definition, is that an ionic bond is a combination of a metal and non-metal. Okay. Whereas a covalent bond is a combination of two nonmetals that are sharing the electrons either equally or non-equally. So we got ionic bonds, metal-nonmetal combination. We have polar covalent bonds where the electrons are being shared unequally. Again, simply because there's a difference in electronegativity between the two atoms that are bonded. And again, I use the example of the general formula AB. AB meaning two different elements, as compared to nonpolar covalent bonds, where I use the example of A bonded to A. Okay, they're the same element, therefore the electronegativity is the same. And also, even though carbon hydrogen is more in the lines of an AB example, because of the electronegativity difference between carbon and hydrogen, which there isn't much to speak of, it is nonpolar, so it's treated as an AA example. Okay. All right. With respect to forces, we had London forces, which we are assigned to molecules that are nonpolar. So all nonpolar molecules, the only force they have, intermolecular force they have, are London forces. They may have polar bonds, that's important, but the polar bonds cancel out, resulting in a nonpolar molecule. Therefore, they have London forces. Dipole force, molecule must be polar, okay? And so either there's all the bonds are polar and they don't cancel out in the molecule, you result in a polar molecule, and therefore they have a dipole force. And then finally, not finally, but the third force is the hydrogen bridging force, and that's a special dipole-dipole interaction, but special only for the case when hydrogen is bonded to either nitrogen, oxygen, or fluorine. Okay. And yes, they do, that is a dipole. But because of that scenario, it's a little bit stronger than simply a dipole-dipole force. So they have their own special category called hydrogen bridging force. And then finally, we have the ion dipole force. Keyword ion should tell you we're dealing with an ionic compound, okay? And the dipole force, most of the time, since we're dealing with an ionic compound, we're dealing with a solvent, which most of the time would be water, aqueous systems. Okay, this page kind of summarizes it pretty good. All right, so you may get this type of table, and you have, you know what I need to do is we're gonna finish this slide at 15 and we're gonna cut it short today. Okay, we'll continue on Tuesday, but let's go through this, and then we'll cut it short here. All right. Indicate the strongest type of IMF, intermolecular force, in samples of these molecules. Okay, so this is where you're given a molecule, you're given this formula there, and what you need to do is determine, is it polar or nonpolar? Now, you may recognize that it may be polar or nonpolar based on what we talked about, or it could be a brand new compound. And if that's the case, then what you're going to do is use the Lewis dot structure, okay? And from the Lewis dot structure, determine the geometry and determine polar bonds within the Lewis dot structure, and determine from the geometry if any of these polar bonds cancel out. And that then tells you whether it's going to be polar or nonpolar, okay? So we have carbon dioxide. Carbon dioxide is one that we talked about at length. The Lewis dot structure, in fact, I just wrote it. They have two polar bonds, but because they cancel each other out, okay, we ends up with a nonpolar molecule. Okay, remember we had that formula. Okay, we ended, that was a general formula. Okay, we ended up with a nonpolar molecule, which means that it is nonpolar. Therefore, automatically, all you need to know that it is a London dispersion force. That's it. Now the PF3, I don't believe we did this in the example, but if you do the Lewis dot structure, it's going to be just like ammonia. And you're going to end up with the following formula, geometry. And guess what? You end up with a lone pair on the central atom. The fact that you get a lone pair on the central atom automatically should tell you something. It should tell you that I got a polar molecule, okay? Very much so. So this species is very polar, okay? Now that it's polar, you ask yourself, well, I got two choices. It's not going to be London dispersion forces. That's not the case, okay? Because it's not nonpolar. It's not going to be the ion choice, okay? Because there's no ionic compounds here. And so the only choice you have is either dipole or London, hydrogen bridging force, okay? Well, if it's hydrogen bridging, you got to have hydrogen, but there's no hydrogen here. So the only choice you got is dipole. Okay? It's not, I meant to say ion dipole for the four choices, which we have no ion here. All right, so the next one is hydrogen fluoride. HF, that's the example of AB scenario, okay? It has a dipole. And so having a dipole means it is polar, okay? All right, so we go through the steps, process of elimination, okay, systematically until you come familiar with all this, and then you're more comfortable with going right to the answer. So number one, it is polar, so we can eliminate London dispersion forces. That's out the window. HF, there's no ions in here, so we can eliminate the ion dipole force. So that again only leaves either dipole or hydrogen bridging. The fact that you see hydrogen there should tell you, let me go check to see if it's under hydrogen bridging. Okay, so that's a possibility. And remember, for hydrogen bridging, there's only three types of compounds that have hydrogen bridging, and those are hydrogen bonded to nitrogen, to oxygen, and fluoride, of which this is one. Okay, so therefore, the force that they have, this one has, HF, is the hydrogen bridging force. Okay. All right. The next one, methane. We have here nothing but, it's a hydrocarbon, nothing but carbon and hydrogen. Remember what I stated. When you have nothing but carbon and hydrogen, then you have a nonpolar species. Okay. Once you determine it's nonpolar, you only have one choice. And that's like we did with the first example, London dispersion forces. Okay. So before we go on with this, keep this in mind. In both cases where we had nonpolar compounds, obviously we ended up with two nonpolars, but the difference is this. CO2 is an example of a nonpolar species with polar bonds. And because the polar bonds cancel each other out in the geometry, it results in being nonpolar. CH4 is nothing but carbon-hydrogen bonds, which means all nonpolar bonds. Okay, there's no polar bonds in there whatsoever. All nonpolar bonds by default is nonpolar, and by default is London dispersion forces. Okay. Now the next one, you see you have an ionic compound and it's aqueous. The fact that you recognize you have an ionic compound and It's AQ physical state. Excuse me. You only have one choice. It's an ion in polar water. Okay, it has nothing to do with polarity. The solvent is polar, yes, but the Ki is ionic, and it's by default in itself polar. So the only choice you have with respect to physical forces is the ion dipole. Okay, now if I were to do a comparison of physical properties, specifically the boiling point, okay, well, I can tell you, anytime you have ionic compound in an aqueous system, I can't use that to compare with another molecule with respect to boiling. Because if you start to boil Ki aqueous system, you're just going to boil water. That's all it is. So you can't do that type of comparison. You're only doing a comparison with respect to physical properties with the other three forces: London dispersion, dipole-dipole, or hydrogen bridging. Okay, and so what we can deduce with respect to boiling point, and that is the temperature in which these molecules will boil, is that HF would have the highest boiling point. Okay, we can't give it an exact number, but we're doing a comparison. We can do a relative comparison. So and these four here, HF would have the highest boiling point because it has the strongest force, the hydrogen bridging force. The next one, as far as boiling point, would come, so the second, so that'd be number one. And then number two, with respect to boiling point, would be the PF3. Okay, why? Because it has a strong intramolecular force, but not as strong as the hydrogen bridging. Okay, so it will have the next one, the next highest boiling point. And the others will come out basically about the same. Number three, as far as boiling point, they would have the lowest boiling point. In fact, carbon dioxide, they have boiling point so low. Carbon dioxide and methane are gases at room temperature. They boil very, their boiling point is extremely, extremely low. Okay. But if we didn't know that, we can make that prediction. HF having the highest boiling point, followed by PF3, and then carbon dioxide and methane would have the third highest boiling point. Actually, we have the lowest of the four here. Okay. We're gonna, like I said, we'll probably do this for the next, probably stop about 10-15 minutes before we're gonna end. And we're gonna stop it here. Slide 14, 15. Okay. Let's stop the share. All right, well,